Okay, so it is better to start from the drag polar condition. So our main intention is to minimize drag in the case of aerodynamic design. That is because the presence of drag is a big critical issue for the designers. So how we can minimize drag is the design aspect, actually, aerodynamic design aspect, so that the total drag, which is the result of parasite drag and induced drag, which is related with even the aircraft wingspan, the aircraft wing configuration. So the Oswald efficiency factor is related with wing design. That is, what kind of wing? Actually, the maximum value of E is 1. For elliptical wing, nearly the value of Oswald efficiency factor is 1. But other wing configuration maybe have less values than 1. So that is the meaning of K. So the thrust force in the aircraft is related to the mass flow rate, the exit velocity. Exit velocity VE means the velocity of exhaust gas. Okay, the hot, high pressure, high temperature gas from the combustion chamber comes through the narrow section of the throat and accelerates through the exhaust. So that the exhaust gas velocity is this one. Another is the exhaust pressure minus ambient pressure times the exhaust area. So exhaust area, exhaust velocity, the mass flow rate of the fuel that are related with thrust. So there are two components of thrust. One is the momentum thrust and another is the pressure thrust. So the momentum thrust is with the mass flow rate. That is M mass times velocity is momentum, as you know. So the momentum thrust and pressure thrusts are here. And this PE minus PA have three different conditions. One is if they are equal, that is called optimally expanded nozzle condition. In some cases, PE greater than PA, and we can get additional thrust from this part. And in the third case, maybe P is less than PA, then it will reduce the momentum thrust also, so that these are what we have already discussed in our optimally expanded nozzle condition, high expansion, low expansion, what you call, means under expanded nozzle, over expanded nozzle, and optimally expanded nozzle conditions are the condition from this equation. So these are the four important aerodynamic forces. The fourth one is the weight. As I told you, weight is the sum of all mass of the aircraft, all mass of the luggage, all mass of the passenger. This sum will give us the total mass. Maybe this total mass may act through one of the particular point called the center of gravity. So, for example, look, for this aircraft, you can see fuel weight, engine weight, wing weight, body weight, payload, vertical tail, horizontal tail, and so on. Again, also there are undercarriage part. Undercarriage means including the landing gears, the tire, the axles, and different undercarriage components are also there. So all these are summed up, and the total resultant will be balanced. Using the weight and the balance method, we can find the center of gravity. So weight is equal to summation of all weights as in the discrete form you can put using summation symbol. And if you want to show it in the continuous form, you can use the integral form. So the differential or integral form is for the continuous system, actually. And if we consider the system as a discrete system, fuselage alone, wing alone, engine alone, and so on, then we use the sum symbol, summation of W as I start from I to N. I from 1 to N gives you the total weight. So this is the weight calculation. And the weight acts through center of gravity. So that is the meaning. Okay, so next, let's see what are the branches of aerodynamics. Okay, the branch of aerodynamics based on different aspects. Actually, one is the flow velocity, another is the flow behavior, and the third one is the viscosity of the fluid which we are using. Based on that, we can classify the aerodynamics. So based on flow velocity, we can call it as incompressible flow aerodynamics and compressible flow aerodynamics. So the air itself at a low pressure, a low speed, the air becomes incompressible. Particularly at Mach number less than 0.3, air is considered as incompressible. That means the density of air cannot vary. Okay, but when the velocity is higher and higher, the air density becomes variable. That means it becomes compressible. So higher speed flow are considered as compressible flow aerodynamics, and that are used for the supersonic, the hypersonic velocities. But in the lower speed, the density of air is considered constant, so that the flow is called incompressible. Compressibility is related with density and the bulk modulus of material. Okay, the flow behavior, classifying the aerodynamics based on flow behavior, it is considered laminar flow, turbulence flow, and transience or transitional flow. So if the flow is steady, then it becomes laminar. And if the flow is turbulent, we call it as turbulent. And in between two, the transition between the laminar flow to turbulent flow is transitional flow. And when we classify it based on the viscosity of the fluid, we can call it as inviscid flow and viscous flow. Inviscid flow means non-viscous flow and viscous flow. And inviscid flow is just a theoretical. It is just a theoretical flow type for a kind of non-Newtonian fluids. Okay. So low speed aerodynamics, we call it as incompressible flow aerodynamics. It occurs at a velocity where the fluid density changes negligible. The change in fluid density with speed is very negligible, especially near to 0.3 Mach number. The flow is considered as incompressible flow. You are familiar with what a Mach number is. So Mach number is just the non-dimensional number, non-dimensional aerodynamic number, which is the ratio of object speed, or particularly aircraft speed, divided by the speed of sound. And as you know, the speed of sound is dependent on temperature, pressure, and density condition, or altitude. It depends on altitude. Why? Because as we go higher altitude, density is varying, temperature also decreasing within the troposphere atmosphere, so that the sound speed is different for different altitude, because it is sound speed is, or you can say it C or A is equals to radical of gamma RT. So gamma is the specific heat ratio, R is the gas constant, and temperature is the varying temperature with altitude. Because as we go each kilometer up, we can find about 6 degree Kelvin decrease, or 6 degrees centigrade of decrease in temperature. within the first 11 kilometers of altitude. So that effect will come into picture through the speed of sound. So you can calculate the speed of sound for every altitude using that radical of gamma RT formula. So Mach number is that. That is m is equals to speed of object divided by speed of sound. So in low speed aerodynamics, it is applicable only for the lower speed with where the fluid is considered viscous forces are dominant. The fluid viscous force is dominant, then we consider low speed aerodynamics. And for the supersonic flows, like the flow of missile, for the flow of rockets, we consider high speed aerodynamics. So that is the second part of your aerodynamic course. Actually, in your syllabus, there are second part of aerodynamics, which you can take it in the next semester. And this high speed aerodynamics is related with compressibility. That means the density of air becomes compressible. That means it can change. Okay. So density is the mass property of an object and it can change. Okay. So studies fluid motion where density changes are significant in this area. And at speed near or above the speed of Mach number 1. So that Mach number 1 is equal to the speed of sound is equal to the speed of object or the aircraft. That may be nearly 341 or 342 meter per second. So it is just critical for designing supersonic and hypersonic vehicles like rockets, like intercontinental ballistic missiles, tactical missiles, okay, which can move in a speed of greater than Mach 1. Okay, it can be Mach 3, 4, 5. Okay, and the engines also for the engine design also we consider this. Okay. And which is governed by the conservation law of mass, momentum, and energy also. Okay. Actually, low speed aerodynamics also governed by these three principles. However, more in general, for high speed, we consider all the terms. Even the density becomes variable here. That rho V A is not constant now. Maybe rho also variable. Anyways. So based on that, how we can classify this aerodynamics, supersonic aerodynamics, transonic aerodynamics, subsonic, transonic, supersonic, and hypersonic. And then also hypervelocity also there. If the Mach is too much higher, we call it as not hyper, but hypervelocity aerodynamics. Not hypersonic, but hypervelocity. So this is in the range of, if the aircraft speed is less than sound speed, we call it as subsonic. For example, 0 to Mach 0.8. Actually, after Mach 0.8 to 1.2, we call this as a transonic transition point from subsonic to supersonic transition. We call it as transonic region. Okay. And when the aircraft velocity is greater than sound speed, that indicates from Mach 1.2 to 5, we call it a supersonic aerodynamics. And then if it is too much greater than, that means if it is greater than Mach 5, equal or greater than Mach 5, we call it as hypersonic. And if the Mach is beyond 10 or like that, we call it as hypervelocity. So these are critical regions. And the design aspect of supersonic, hypersonic, and hypervelocity are different than the subsonic and the transonic flights. Okay, so we must take care of these points. And this is the definition of Mach number. Okay, velocity of aircraft divided by velocity of sound gives you the Mach number. So look, this is the flight region. We classify the flight region based on the Mach number. Look, you have a nautical mile. What does it nautical mile mean? One nautical mile means 1.852 something like that kilometer. 1.85. 1.85 kilometer is considered as one nautical mile. So there is a nautical mile is given. There is a Mach number is given. So on that you can find for the first 0 up to 0.3, you can call it as incompressible flow here. On that, this is small drones, small aircrafts, helicopters, or some kind of ammunitions. They can flow, or they can be a bomb actually. This one is a bomb, so they can fly within this incompressible flow condition. Then from 0.3 up to some region, we can say subsonic flow. Subsonic. Incompressible flow, subsonic flow, from 0.3 up to 0.8 nearly, which is called subsonic flow. This is another flight region with different color you can observe here. On that, you can find the military aircrafts, commercial aircrafts, like they can flow on that. Again, after 0.8 up to 1.2, you can find magenta color here. There are also those huge transport aircrafts, and some aircraft can fly here. That's the region is called transonic flow. And then after that, you can find 5 point something, from 1.2 to 5 point something, you can find supersonic flow. This is supersonic flow region with red color. And light yellow color, or I can say it as white color here, indicates hypersonic flow. Hypersonic flow is from that 5 point something up to 10 point something. So hypersonic flows are there. Then beyond that, it is called hypervelocity flow. The yellow color indicates hypervelocity. So this is the regions. Actually, we call it as flight region. What is the characteristic of aerofoil in different regions? For the flight, Mach number less than 0.8. Within that transonic, subsonic flight, your aerofoil is characterized with linear flow. You see, the stream lines are very linear. There is no turbulence on them. But actually, this is what we call subsonic flow region. Okay. And then if the flow is in between 0.8 and 1, there is also a transonic flow with Mach nearly less than 1 is. On that, you can find shock wave here. Okay, it is now, the stream lines are not laminar kind of flow, but you can find this kind of shock wave. So the presence of this shock wave creates two regions in the aerofoil. The front region is in supersonic and the back region is in subsonic. So in the front, Mach greater than 1. At the back, Mach less than 1. So that condition is kind of critical condition. And within this region, there is also another important aspect is there. This is called the drag divergence Mach number, we call this Mach number. The Mach number from 0.8 up to 1 is called drag divergence Mach number. Why we call it as drag divergence Mach number? 0.82 is considered as a critical Mach number on which, from that point onward, the drag becomes abruptly shoot up to the maximum point. And finally, it reaches to the sound barrier point, so that that point we call from 0.8 to 1 is drag divergence, Mach number, or the drag becomes very maximum and the flow becomes complex. Why? Because there are supersonic region and subsonic region in front and the back. So the flight within this Mach is not advisable in the professional flight conditions. Another is transonic, that 1 up to 1.2 is also another. It might have another shock wave. The shock wave is bow shock created in front of the object. And there is also trailing edge shock wave also happen here. Two types of shock waves. The trailing edge shock wave at the behind of the aerofoil and the bow shock wave. And it is very thick shock wave happen in front. So two types of characteristics are there. So just after bow shock wave, you can find Mach less than 1. The flow is subsonic in front, and behind of the aerofoil, the flow is Mach greater than 1, indicates supersonic. Still, it is complex. So professional pilots are not advised to fly within 0.8 up to 1.2 Mach number, because that the condition of the shock wave is very complex here. And then if the Mach is greater than 1.2, there is attached oblique shock wave happen here in front. In front of, this is the wedge of the object, or you can consider aerofoil. And in front of the aerofoil, you can see attached shock wave. The shock wave is directly attached to the object. But here it is detached. Shock wave is in front, somewhere far away in front. Okay, here it is directly attached. And then once the streamlines pass here, at the junction somewhere, there is also expansion waves also there. Not only oblique shock wave, but expansion wave. Okay? This is expansion wave at the behind. So this kind of, when we are having maximum Mach to the Mach greater than 5, fully the shock wave, the oblique shock wave will be attached to the body. And this attachment of the oblique shock wave to the body creates heat on the surface of the aircraft itself. So that the aircraft structure must be designed for the heat consideration also, not only the stress and the strength consideration, but heat also will come into picture. Because the heat produced from this attached shock wave to the body creates high heat and that heat will be transferred into the internal structure, and then it will collapse the structure or the aircraft. So that this all must be in your mind when you are designing an aircraft for different flight regions. So when I say shockwave, I'm not going to explain you all the shockwave type, but just to give you a highlight, it is a very thin region in supersonic compressible flow, across which there is large variation in the flow properties. At the point where shockwave happen, flow properties are immediately abruptly changed. Density change happen, velocity change happen, Mach happen. So that we can see immediately now. Because there are variation occur in such short distance, viscosity, heat, conductivity play dominant role on the structure of the shock. So look, this is the pattern of light in subsonic speed. In subsonic speed, you can observe this kind of pattern of light. So this is the point where sound is emanating, and these are the sound waves which are circling that are called pressure waves. Okay, so these pressure waves. But as Mach reached to 1, that is objective speed is equals to sound speed, then what happened? The aircraft is coming out to this edge. All these elliptical shapes are coming back to the aircraft. And finally, when it gets into supersonic, so you can find Mach cone even here. This is called Mach cone. That actually, this cones indicates what? If you observe helicopter, you can hear the helicopter sound before the helicopter arrives to you, right? As you see a helicopter from far distance, you can hear its sound before. But if you take supersonic or an aircraft which fly with Mach 1, you can observe the aircraft uh, exactly above your head. When it comes to your heading, you can observe. Before that, you cannot see. And if the aircraft is in supersonic, you may not observe the aircraft. It can go far away from you and you can observe it later. That is because of this kind of pattern of the Mach. For helicopter, you can hear its sound before you see the helicopter. For aircraft which is moving in Mach 1, you can observe it just at the top of you. And for aircraft having Mach greater than 1, you can observe it after it passing you, because sound speed is less than the speed of that object. That is the logic behind, and the Mach cone formation is that kind. And what we are hearing is from the formation of the Mach cones. It is just particle disturbance or the pressure disturbance. What we are hearing is the pressure disturbance. So these are just a simple explanation of normal shock wave and oblique shock wave. So for the normal shock wave, the flow properties, these are called properties. For example, Mach, velocity, pressure, density, temperature, enthalpy are there. Okay, so this is the region where which separates. That is what we call shock wave. So assume that this is shock wave. So before shock wave and after shock wave. Number 2 indicates after shock wave. So Mach is greater than 1 at the formation of shock wave, or for oblique normal shock wave. After shock wave formation, Mach is less than 1. Velocity is there, so V2 is greater less than V1. Pressure. So this is just the properties after shock wave and before shock wave. And this is also in the case of oblique shock wave, having oblique angle beta. Okay, you have oblique angle beta. So the property before the shock wave and the property of after shock wave are here. So this is just to elaborate what is the shock wave and the different types of shock wave. So the flow, based on the flow, actually we classified aerodynamics based on flow pattern, based on the compressibility, based on the viscosity. So the second classification of aerodynamics is based on the flow behavior. So based on that, laminar flow, turbulent flow, and transitional flow are the three important classifications. Okay, so I'm quite sure you learn this thing in detail in your fluid course, so that I can leave it for you. Actually, we have left 10 minutes for this session also, then we can continue. Again, based on the viscosity, we can classify it non-viscous or inviscid flow and viscous flow. So these are also another classification pattern. So why we are, what is the application of aerodynamics in the real world? One is for the design of aircraft. Fundamentally, what we are learning this aerodynamics is for the design of aircraft, for the design of spacecraft, for the design of missiles. It can be any kind of aerial vehicles. Okay, so it is essential in the design of wings, fuselage, control surface to optimize the performance and efficiency. Okay, so fuselage design needs critical aerodynamic concept. Wing design needs critical aerodynamic knowledge. Control surface. These are like the flaps, aileron, and other control surface like slats and slots. Okay, high lifting device design. And optimization of performance is of different performance parameters are, as I discussed, like takeoff performance, landing performance, climb performance, descent performance, again, cruise performance of aircraft. And finally, for the efficiency, efficiencies are related with the fuel consumption rate. Efficiencies are related with arriving to the destination within short time. That is what we call endurance. And covering long distance within short time. So that is the meaning. So aeronautical engineers are expected to design aircraft wing, fuselage, and other components to maximum lift and reduce drag. So drag reduction is one of our aim. So by careful shaping and optimizing the structure, the engineers can improve fuel efficiency. They can improve stability and the maneuverability. That means maneuverability means what? The turning of aircraft in short radius. Okay, the rate of change of direction. Okay, the agility, flexibility of the aircraft to perform certain tasks that are called maneuverability. Okay. Automotive engineers need also aerodynamic concept for these competition aircrafts, no cars in the area of sport cars they need. Again, the bicycles and motorbikes, they need aerodynamic slender design. Okay, streamlined design. Okay. So by reducing the drag, they can improve the overall speed, handling, and fuel economy. Okay, so streamlined shape spoilers. Spoilers are required actually. Spoilers, the main intention is to increase drag actually, and other parameters. Architectural designers also design their buildings with the context of aerodynamics. Okay, so they consider aerodynamic force and when designing building bridges and when sport stadiums. Okay, sport equipments like soccer balls and golf balls. Okay, these also are they need aerodynamic design. So in general, aerodynamics is a scientific discipline that explores the interaction between object and gas, that particularly in our case it is air. And its principles are very vital in the design and optimization of aircraft, automotive building, and various objects. So understanding it, harnessing the force of drag and lift. And so this is why we need aerodynamics. So in the modern aerodynamic concept, the hypersonic and supersonic and hypersonic, including the hypervelocity designs are the fundamental because there is an idea that related with intergalactic flight. So in order to design intergalactic flight, even though it is not achievable yet, but for future, people are working on it. For that, we must design an object which is moving in hypervelocity. Okay, so for that, many scientists are working on the Navier-Stokes equation. We'll see what that Navier-Stokes equation, the Euler equation also, the two-dimensional Euler equation of the fluid and the three-dimensional Navier-Stokes equations are also under investigation because for the Navier-Stokes equation, there is I am not quite sure whether exact solution is obtained or not. So the history of aerodynamics also is characterized by the contribution of many scientists. Actually, I don't want to go through the history of aerodynamics because it takes more time. you will read it. And what are the tools and the techniques used for aerodynamic analysis? As an aerodynamic student, you must understand what is wind tunnel and how we can measure the aerodynamic coefficients using wind tunnel test. That is an experimental test method on which air is blown over the model, and we can take the flow property or the aerodynamic property of the model. Look, this is a model from the NASA. So this model is placed in the wind tunnel section, and the air is blown from some point, and it passes through the object, so that the object is now stationary and the air is moving. But in actual aerodynamics, aircraft is moving, but air is stationary. So aircraft enter into stationary air and creates the air, the interaction between air and the aircraft. But here, in the opposite direction, the object is stationary in the wind tunnel at the test section, and then the air is blown to the object. So that gives the aerodynamic coefficients like lift coefficient, drag coefficient, moment coefficient, and so on. Another method is the numerical method, which we use finite element method, that is CFD, computational fluid dynamics method. So on that, you can use numerical tools with high computational power computer. And you can simulate the aerofoil of different shape. And the third one is the actual flight test method. So on this actual flight test, the flight engineer or the pilot will go with the flight attendant or the assistant. So the flight attendant will take all records of every point in the flight condition, and then that will be checked with respect to the aircraft performance. So these are the methods and the tools which we use to analyze aerodynamics. So the history of aerodynamics, you will see it by yourself in the ancient time, how it is started. Aristotle and Archimedes, they studied. Sir Isaac Newton, Daniel Bernals, Leonardo Euler, Navier Stokes, George Kelly, the father of aircraft, or the father of aerodynamics, Francis Herbert, Charles Randall, Otto Lilienthal, this glider flight. So the one who passed away because of the failure in the aircraft. And Wright brothers in the 20th century, and others also are contributed on it. So this is all about aerodynamics, introductory part. And then we'll directly enter into fundamental aerodynamic variables and their expressions. So I think time is over. It is less than 1 minute is there. We'll rejoin after 15 minutes. You can take 15-minute break and we'll rejoin it. Right? ሰምታችሁኛል? 15 ደቂቃ በኋላ እንገናኛለን። አሁን ማረፍ ትችላላችሁ። ኦልሬዲ እየጨረሰ ስለሆነ ማለት ነው።